Finally, you often get the question, in my descriptive table 1 in my paper, should I present the means or should I present the medians? Well, you'll see if you read a lot of the medical literature that most people go with the means. I think most people feel very comfortable with the means. That's what they're typically used to seeing, so a lot of authors will present means. It turns out, however, there are cases, a lot of cases actually, where it would be better to report the median, because if you have skewed data, if you have extreme values, as we've seen, those extreme values can influence, can affect the mean, and so the mean might be misleading, whereas the median doesn't get affected by those extreme values, so the median might be a better representation in that case of the center of the data. So let me just illustrate that. I'm going to harken back now to one of the teasers that I presented at the beginning of this week. I had presented some hypothetical data about a randomized trial on diets. So we had 20 dieters who were randomly assigned to follow one of two diets, call them Diet 1 and Diet 2. Again, these are hypothetical data made to illustrate a point, but they're still interesting. So it turns out here's the results of that trial, as I mentioned in the teaser. So group 1, those on Diet 1, lost an average of 34.5 pounds. Group 2 lost an average of 18.5 pounds. So both dieting groups were highly successful. These are really good results for a dieting trial. But if you were just to look at those numbers, you'd probably say, oh, well, if I've got patients and I want to figure out what diet to put them on, based on these numbers, I think I'm going to put them on Diet 1. Diet 1 looks better, right, if you just look at the means. Is Diet 1 better, however? Well, let's dig down deeper into the data to answer that question. So here's the histogram. I'm going to start with Diet 2. Here's the histogram of the weight loss from the 10 dieters in Diet 2. So as I mentioned, the mean was 18.5 pounds, an 18.5 pound loss of weight. The median was a weight loss of 19 pounds. And if you graph it on the histogram, you can see that they're pretty well clustered. Everybody's losing some amount of weight, and the variability isn't very high. Now let's turn to the histogram for Diet 1. Okay, you can see that this is made up data, but you know, this could really happen. So here's the histogram from Diet 1. So what do you notice? So the mean is a weight loss of 34.5 pounds, but the median is only a weight loss of 4.5 pounds. And of course, the reason is that we have this extreme value out at negative 300. Somebody was very highly successful on this diet and lost 300 pounds. That 300, that negative 300, when you average it in with the other 9 values, has a huge influence on the mean. It completely draws the mean to the right, and it's misleading, right? It makes the mean look much bigger. The median here is really a better representation because most people weren't losing anywhere near 30 pounds. Most people were losing 4 or 5 pounds. Let me just show you the raw data. There's only 10 data points in each group, so I can actually show you the raw data. So here's the raw data from Diet 1. Here are the weight losses for Diet 1, and I've ordered them from the least weight loss to the most weight loss. For Diet 2, you can see the same thing. Here are the raw weight loss values. Now, if you look at the raw data like this, you suddenly get a different feeling for Diet 1 versus Diet 2, right? If you're looking at this raw data, you might change your mind now and actually want to recommend Diet 2 for your patients. Because what you can see is that on Diet 1, 1 out of 10 people lost a huge amount of weight, but everybody else's weight loss was non-existent or moderate. Whereas in Diet 2, everybody was highly successful. Everybody lost a good amount of weight. So it was a very, you can see that it was successful for everybody. So it changes your opinion when you see all of the data like that. Now, when you're actually going to analyze these data and to run a formal statistical test, we haven't talked about any formal statistical tests, and we won't get there for another couple of weeks, but the way that your instinct might be to compare those groups by just comparing the means, the 34.5 versus the 18.5 pound weight loss. If you did that, you would compare those two means with a test that we call a t-test, some of you may have heard of. If you do that, you will find that there is no significant difference between the groups. So what you need to compare in this case is not the means, but you need to compare the medians. You need to compare the data using a ranked data procedure, something called a non-parametric test. And don't worry too much about this terminology right now. We're going to talk a lot about non-parametric tests in a future week. But some of you may have heard that term before. So this is an example. What I'm going to show you now is an example of a non-parametric test. That just means that we're going to be ranking the data and running tests on the ranks of the data rather than the raw values. And it's the test that I'm actually going to run now. I'm going to tell you the name of it only because it has a very informative name. It's something called the Wilcoxon rank sum test. And don't worry about the details of that yet. We'll return to that test in another couple of weeks. But it's very easy to figure out what the test does because it is a rank sum test. So literally we're going to rank the data and then we're going to sum the data. And that part is easy to understand without knowing anything about non-parametric tests. So we're going to do that. We can do that right now. So let's rank the data. So what do I mean by ranking the data? So what we're going to do is we're going to order the data from the lowest weight loss, the worst weight loss, to the highest, the best weight loss. And for the moment, we're going to rank the data ignoring which group people are in. So there are 20 people here. The person who lost the least weight, which was the person who gained 4 pounds, they're going to get a rank of 1. The person who lost the most weight, which was the person who just did really well and lost 300 pounds, they're going to get a rank of 20. And we're going to rank everybody in between. And again, for the moment, we're ignoring diet. So you can see that most of the low ranks go to diet 1. The 6 lowest ranks go to diet 1. The 6th lowest person lost only 5 pounds, and then we jump to diet 2. The 8-pound weight loss in diet 2 was the 7th lowest, and then the -10, the 10-pound weight loss was the 8th, and then we jump back to diet 1 to give the 9th rank, and so on. So you can see that now we're treating everything rather than using the underlying values like the -300, which is so highly influential. We're giving everybody a rank, and the rank values, you can see everybody, it's only 1 unit apart, so that's going to have less influence on the statistics. Notice, however, though, that we did not take that 300-pound weight loss and throw it out. That would be a mistake because there really is somebody who did have a fabulous success on diet 1 for whatever reason. That person gets counted. They get the best rank. They get the 20. But the 20 has much less influence on the statistics than that -300. That's the idea. So we rank everybody from 1 to 20, ignoring which group you're in, and then we sum up the ranks within each of those groups. We just add them up, literally sum them up. So we take the ranks from diet 1 and we add them up. We come up with a sum of the ranks of 73. Do the same thing with diet 2. We come up with a sum of the ranks of 137. Notice that 137 is much bigger than 73. Where we need the formal Wilcoxon sum rank test is to actually say whether or not that 137 versus that 73, whether that's a difference that could have arisen by chance, or does that represent likely a real difference between those diets. And so when we actually apply the formal Wilcoxon sum rank test, something we're going to learn in a few weeks, to say whether or not 137 is really different than 73, in fact, we get a significant p-value here. So in fact, when you apply the correct statistical test here, you find out that diet 2 is significantly better than diet 1. Exactly the opposite of what you might have concluded if you had just looked at the means.